ZT. Reviewing when we choose our weak classifier for AdaBoost, what we want to do is we want to choose a weak classifier that has small weighted error, okay, with respect to this distribution dt. So those examples which have been hard before will play more of a role in this term here, and so when we add a new weak classifier to our ensemble of classifiers which we're combining, the later classifiers will focus on examples which we've had a problem so far. The final ensemble of classifiers, we're building each classifier, and that ensemble has this following weights. Classifiers which did generally well have large weight because this was 0 at their near 0. So this goes to infinity. For things which are wrong, this goes to a half, and so this goes to 0. So the final classifier we're learning is just this linear combination of the weak classifiers. Okay, let's see if we can get a feel for what it does by looking at this pictorially. Okay, so one of the reasons we do decision trees is because a standard weak learner that people use often for good results are decision stumps, where a decision stump is simply a single axis parallel hyperplane. Okay, so you can imagine we as a set of weak learners, we could imagine all the possible different decision stumps which we could choose. Okay, so if we have m points and we have d dimensions, there's something like d to the m possible weak learners. Okay. So suppose our data set looks like this. We have some plus points and we have some minus points. And we want to now go ahead and choose a weak learner which minimizes the classification error. We start out, we're on the first trial, all the weights are uniform, so we just want to choose a stump which makes the fewest possible mistakes. I think we can persuade ourselves that we can do no better than 3 possible errors. Okay, so this thing correctly classifies the pluses, then correctly classifies these minuses, but fails to correct the pluses. So its error is 30%. Its weighted error, the weights are uniform, is 30% on the data, and the alpha, if I plug that in, would correspond to that. So now what we do, if we recall, we go back and we reweight. So each of our given m points now have new weights. So things which we've done well on get their weights reduced. Things which we've done poorly on get their weights increased. And so that's what we're showing graphically. In the next picture here, we did equally well on these 7 points, and we did equally poorly on these 3 points. So we're visualizing larger d values with larger signs there. So this plus is much larger. Okay. So now we want to choose a decision step which minimizes the weighted square error of, the weighted classification error of these examples. And I think you can persuade yourself that it's not a hard thing to compute. You can go ahead and you can check all d to the m possible weight classifiers. You just compute that weighted error sum and see which of those is minimal. It's going to be one of those d to the m. There's d to m possible things to check. So it's something you can go ahead and check. You can also persuade yourself, this isn't quite the weak learner guarantee, but if you use these decision stumps, you have to, the error on it can't be more than 50%, because if it was more than 50%, you can always use the negative of it, and so it's less than or equal to 50%. So you'll always find something that's 50% or better. The question is, if you continue to do this for a long time, can you keep it bounded away from 50%? That's the tricky assumption, which you've observed you may not be able to meet in practice. Okay. Okay. So this was our first decision stump. So now we want to find a new hypothesis with small weighted square error. So now the claim is that this new hypothesis has small weighted square error. If we look at absolute square error, we can see that absolute square error is pretty large. It's 5. So it has larger absolute square. Sorry, the weighted square. No, the weighted square is the same. I mean, the non-weighted square is 3. These are mistaken examples. But you know, this weighted square the weighted square will be less than 30% because we have these high weight examples here which contribute more to the square error, and so the overall weighted square error would be smaller than 30% here. And so here our weighted square error is 0.21. Then we go back and we go ahead and we apply equation 18 again, reweighting the examples. So looking at this diagram, we can kind of see that there's 3 classes of examples. There's this plus and this minus. These we've always gotten right all the time, and so they probably have the smallest weight of all. They're relatively easy for us. But now we're going to have some contribution from these examples. These examples were wrong this time. They get larger weights. Our overall weighted accuracy was higher, and so even though these 3 are larger than those 2, these 3 are even larger than those were. Okay. So that That's how we generate our second decision stump. Third decision stump, these are quite large, so we know that we really want to get these correctly. These are somewhat less high, so we'd really like to get those correctly. So right now, our number of mistaken points is still 3 in absolute error, but our weighted error is much smaller here, and our weighted error is 0.14, and this plays a large role in our final classifier. Its alpha weight is large. Okay, so now we've found 3 different decision stumps, which we can all see improve on the hypothesis. They all do slightly better than 50%, or significantly better than 50% in weighted error. So now what we're visualizing is h of x is equal to final h of capital T. That's just the sum of alpha t. So alpha 1 h1, alpha 2 h2, alpha 3 h3. So these were the alpha coefficients that we computed. These correspond to the decision regions of each of the small weak learners. If we sum these 3 weak learners together, we see that on this new data set, by example, I will have correctly classified the points. So this is a pictorial representation of the idea of boosting. Questions about how this works or worked? What we're going to go ahead and prove now is we're going to prove that if we follow this procedure, we can always find weak learners bounded away from 50%. Then our training error, i.e. we'll be able to find a linear combination of weak hypotheses with 0 training error, as we've done in this case. Okay, so I'm going to prove that the training error goes to 0 as we get more weak hypotheses with the boosting algorithm. I'm not going to prove anything directly about the testing error. We're just going to at least persuade ourselves that if we can keep finding weak hypotheses, and this means that this algorithm designed for combining them will find one with 0 training error eventually. Okay, so on the left-hand side, we have the unweighted training error. Now we're observing that this term is equal to the product of the normalizations on each trial, whereas if you okay. So let's well, the first side of the inequality we can check by if hx does not equal xy, this is negative, so this is positive, so E is more than 1. If this is 0, then when this is negative 1 over E is also more than 0. So the first inequality is easy. Second inequality, so this first inequality just follows by substituting in 1 and minus 1 and seeing what happens. Let's look at this product. So recall that dt is defined recursively. So given this recursive definition of dt, we know that capital D, capital T of I is equal to the product of zt to t times the product of this 2t e to the minus alpha t yi hxi. Okay, and then they were initially weighted at 1 over m. So what I've done is I've just plugged in, so each time I kept multiplying, so capital dt is just equal to the product of all these terms. So the product of exponentials is equal to the sum of exponentials. This is we're doing it over small t, big T. So this is equal to 1 over m e to the minus alpha t Okay, so e to the alpha t h t x t, we we define to be f. So if I go ahead and substitute in, this gives me 1 over m e to the yi f of x product over zt. We can just sum this over all the different dt's. So we get the sum of dt, d capital T I equals 1 to m is equal to 1 over m sum e to the minus yi fxi, where we're summing over the examples, product of zt. We summed over all the dt's, that's the distribution which we keep normalizing, so it's equal to 1. And so now we can just multiply out by zt, and this gives us our equality that we're looking for. So if we choose alpha t and ht to minimize zt, the training error will be minimized. See that by looking at this, which bounds the training error. So so in practice, what we've done with our boosting algorithm is we've had hypotheses that classify. They go to -1 or 1. In practice, people often, you can get better success with different kinds of classifiers that have a range, rather than just saying you're sure it's a label or not sure it's a label. You give some range of confidence. But we're not doing that, and since we have chosen things are 1 or -1, then it's easy to check then that how we're getting these updates alpha t is by this choice of alpha t. So let's see how we do that. Okay, so as we did before, this is our definition of normalization. Remember, we do the update. Each of our weights dt plus 1I becomes that, and then we sum those weights and we divide out by zt. So if we, that's one way of looking at the value of zt. Now we're going to use the fact that ht returns binary values. So you can recall that epsilon t is our weighted training error. So epsilon t is the sum from I equals 1 to m over m examples. Our weight, eti, our weight at time t, times whether we got the example right or wrong. Okay, so when we make a mistake, yi is not equal to htxi, and it's -1 because it's either 1 times -1 or -1 times 1. So we get e to the alpha t. We split the sum. This is the examples which we've made the mistake on. Examples which we are correct, yi and htxi match in sign, so we get e to the minus alpha t. And we then sum over the correct examples. So if we look over here, we have just the definition of epsilon t, so we get epsilon t alpha t, and then likewise here, we simply have 1 minus epsilon t times e to the minus alpha t. So if we want to choose the value of zt, which will minimize our upper bound on the classification error, we just need to differentiate with respect to zt. So quickly, what happens here is, I guess, d of zt with respect to alpha t. So we get et times epsilon alpha t, because epsilon t is a constant. E to the alpha t is just e to the alpha t when we take the derivative, minus 1 minus epsilon e to the minus alpha t. Now we can set these equal to 0. E's and epsilons look terribly similar. You read what I'm writing, hopefully. So we'll set this equal to 0 and solve, and we get, I'll probably bring that to the other side. We get 1 minus epsilon divided by epsilon is equal to e to the 2 alpha t. Okay, so if we take a log, we get 2 alpha t equals log of that, and then multiply both sides 1/2, and we get our update for, that's how we set alpha t. Okay, questions so far? So we're just trying to argue that that boosting will combine our hypotheses in such a way to minimize the training error. So now we're just going to go ahead and substitute in alpha t 1 minus half log 1 minus epsilon t over epsilon t into zt. So what happens when we substitute in? Hold on, typing to it. Maybe I'll do it on the board. So if we substitute in, we bring the 1/2 inside the log, so that becomes like a square root of the term on the inside, and so we get epsilon t, e of the log is just the thing itself, times square root 1 minus epsilon t divided by epsilon t, and then the same sort of thing on the other term, plus 1 minus epsilon t. We substitute it and we get square root of negative. We have a negative on the inside, so we have epsilon t over 1 minus epsilon t. Substitute, we bring epsilon t inside again, bring it inside, we have a square, square in, square cancels with the bottom, so we have a 1 minus epsilon times epsilon. Same thing happens here, so we have an epsilon times 1 minus epsilon, and the square root, we sum them both up, and we have our first part of the equality. Okay. So we're assuming, so the overall assumption that we want to make on these weak learners is that for this weighted distribution, we can always find something with training error bounded away from a half. So here the assumption is gamma t is how much we happen to be bounded away on that particular trial. Okay. So just substituting in this gamma t for 1 minus half epsilon t, we get this term here. Okay, finally we get to bound the training error. So the training error, as we showed before, is upper bounded by the product of the zt's. We've shown that the zt's are equal to the product of these square roots, which is less than or equal to e minus 2 times that sum. And so the observation is then finally, is if in the training error, if these gamma t's are all larger than 0 by some amount gamma, i.e. we do better than 50% by, say, we always get 52% accuracy, then gamma's 0.02, then the error drops exponentially fast in t. As t increases, we see that the error must go down exponentially. Okay. So the training error is bounded. Okay, so here I'm giving you an example given by the creators of AdaBoost. So how do the training error and test error depend on AdaBoost? Well, a normal thing we expect from maybe test and training. We keep adding on new hypotheses. Is that at some point we keep training, and the training error keeps decreasing, but the test error increases. This is the usual story. Surprisingly, what happens often, it's not going to happen on every sort of data set with AdaBoost, but an early observation which surprised many people with respect to AdaBoost is that even after you reach zero training error, i.e. if we're counting the misclassification error, not the weighted training error, so we can reach zero misclassification error, but we still have some sort of weighted training error, we can keep training AdaBoost at this point. In general, it's seen that the test error for many problems, even though this certainly isn't going to be true for every problem, particularly if your weak classifiers aren't particularly weak, i.e. they come from a complicated hypothesis space, the test error continued to decrease. An explanation which was given for this phenomena, which we're not going to go into real detail, but much like you do with a support vector machine, we can define an analogous L1 margin, and what's happening with continual training, it's like you're solving an optimization problem, and that margin tends to increase. So what is the margin? The margin of a individual training point is f of xt is just alpha t, h t of xt. So alpha t, h t x t is outputting a real number, even though because alphas are real numbers, h's are outputting ones or minus ones. If we call this the margin, where yi is the where yi is the label, fx is the value which we give xi. After we finish boosting, we normalize the alphas. We call that the margin. It turns out if the final classifier has a large margin, which there's not a guarantee that it'll have a large margin, then you run your data. You run some given t rounds of boosting. We look at our value of the margin. If this margin is bounded above by theta, then our generalization error on the new data tends to be bounded by this term. What is this term? So first, before we get to this term, if you've trained your data so that you fit perfectly, this first term will go to 0. This term is some measure of the complexity of our set of weak learners. if it was just the set of decision stumps that we tried, D would then be something like log m. The generalization error tends to go down at a rate of square root of m. So our test error will go down by a rate of square root of m divided by this if we achieve large margins and constant, which depends on the margin. So what's the take-home message of that? The take-home message of that is if you have enough data points, your generalization errors decreases at a rate of square root of m if you manage to find something with large margins, which you won't have necessarily found. So, not interested in examining you on these generalization bounds, but for those of you who are interested in it and want to understand the details, a good first paper to look at is this boosting approach to machine learning. That'll go over to the details of that bound if you want to understand in what sense we can bound the generalization error, perhaps answering the question in more detail than I want to address. Okay, so what's the summary for boosting? So, given you have something that can come up with these weak learners on all the rounds of boosting, bounded away from 50% error, boosting can find a linear combination of these weak hypotheses with small training error. With sufficient additional assumptions, you can prove some guarantee on the test error, which should hold under a high probability, which I don't want to go into too much detail on. Questions? Yes?
Remind us that the VC dimension is the number of possible partitions that our functions can make on the data, something like that.
So an easy bound for the VC dimension on a finite dimensional hypothesis space is log the number of the potential hypotheses. So if you have if you have decision sums, log 2 over n is an upper bound on the VC dimension, but the VC dimension, which I'm not sure if Massey is going to do this year or not, is it's a measure of complexity which basically describes, it's hard for me to describe quickly, but how many functions you can classify all possible training sets on. It's also exactly, it's a lower bound for the mistake-bound model in online learning. Asking at the VC dimension. Other questions? Okay. Let's take a 10-minute break. I'm running quick today. I think I will return and do an example from online learning that we didn't get to last time.